So I've pulled out two questions from a number of students on set theory. And I thought that before I go through these questions, it might help students to, have some understanding of the fundamentals of set theory, okay? So I'll not go into details, but at least the material that is relevant to answering a question like this. So let's see what I mean by this, okay? So in fundamental set theory and Venn diagrams, we have something we refer to as the difference of sets, okay? So what's the difference of the set A and B? We define the difference of set A and B, so let's start by drawing a Venn diagram there. So suppose that is a set A and the other one is a set B, all inside a universal set. Of course, I'm hoping that we understand what we mean by this. So we have two sets A and B, which are subsets of the universal set U. Now, we will name some regions within the set A and B. So let that region there be represented by X, the central one there be represented by Y, and that other region be Z. Then we can say that set A contains two elements X and Y. So we can say set A there. All right, so set A, to represent a set A, we have to use those squiggly brackets, sometimes called braces. So the set A contains elements X and Y. The set B contains elements Y and Z, okay? And the set that of all elements that are outside of A, so if you look there, the elements that are outside of A, and we are assuming that all the elements are either in A or B, there is nothing outside. Okay, so the elements that are outside of A, there is X and Y are in A, so the elements outside A is Z, and the elements outside B must be X. So Y and Z are in set B, and so X is outside the set B. So this is the complement of set A refers to the elements outside of the set A. The complement of set B refers to all the elements that are outside the set B, like that. So if we understand this, then life becomes very easy when we meet questions referring to sets, okay? All right. So how do we define the difference of set A and B? So the difference of set A and B is the set of, so when we say difference of A and B, in this case I mean A minus B. So the difference of the set, which we'll refer to as A minus B, refers to all the elements that are in set A but outside set set B, okay? So all the elements that are in set A but not in set B are referred to as the set A minus B. So the difference set A minus B refers to all elements that are in A but not in B. So if you look at this, which are the elements that are in A but not in B? Well, clearly Y is in A but also in B, so Y does not qualify. Z is not in set A. So we want only the elements that are inside the set A but not in set B, and that leaves us only with X there. So the elements of set A that are not in B sometimes expressed like that. This means inside A and not in B. So in A and not in B. So X there is in A and not in B, and therefore that is the set A minus B, or the difference of the set A and B. In the same way, we can talk about the difference of the set B and A. That would be B minus A. But before we move on, let's just see what, let's look at an example of this. We want to find the difference of set A and B. So let's, as I've already defined it, all elements that are in A but are not in B. Let's look at an example. Okay, so that's just to indicate that I'm referring to that region there. All right, now suppose that the set A contains elements X such that X are natural numbers that are less than or equal to 8. That simply means natural numbers are counting numbers from 1 to 8. Okay, so I could remove that. Set B, on the other hand, is 3, 5, 6, 7, 8, and 9. Of course, like I've said, this is just another way. I put that there just to remind you of how to read that. So the elements of set A, so we can read this, that the element of set A are such that they are natural numbers that are less than 8. Natural numbers start with 1 upwards, so 1, 2, 3, 4, and so on. So they are less than 8, that means from 1 to 8, okay? So I can remove that and put the other way of representing that set. So you can see you have too many numbers. So when you have too many numbers like that, the set notation that I used earlier can sometimes be better. So sometimes it's better to write that than to write this, especially when the number of elements in the set are too many like this, okay? So this is our set A and that's our set B. What we want is the difference, or set A minus set B. So set A minus set B, or the difference of set A and B, refers to the elements that are in A but not in B. If we are going to get this, maybe a good way to do that is to represent this on the Venn diagram. So I'm going to remove those and then just try to write these things out ourselves. So which are the elements in the three different regions? I'm going to start with the inside, what we refer to as the intersection. So elements that are in both A and B would be, if you look carefully, 3 is here and there. So 3 is one of them. So we see 3 here is going to fall in, 3 and 3 here. We see there is a 5 there and there is a 5 here. There is a 6 and there is a 6 there. There is a 7 and a 7, and I think the last one there is 8 and 8, like that. So those are the elements that are in both sets. So I'm going to write them in here. So we have 3, 5, 6, 7, and 8. So I can write here 3, 5, 6, 7, and 8 are all elements that are in both set A and B. Which elements are inside set A? I can see 1, 2, and 4 there. So I can place my 1 will fall there, 2 and 4 there. And elements that are in set B but not in set A, I see there is only 9 there. Okay? I believe I'm done. And now with that information, if I use the definition of the difference of the set, I can see that the set of elements, the elements that are in set A but not in set B are 1, 2, and 4. Okay? So therefore, I can write, let me remove this. So we can write that A minus B is the set of elements that are in set A but not in set B, and that is just 1, 2, and 4. Okay? I hope that's clear. We could use the same thing to reason the other way around. So elements of set A minus B is simply 1, 2, and 4, like that. There's nothing difficult about this. Let's see set B minus A. So in the same way that we found A minus B, we can talk about set B minus A. So set B minus A is the difference of set B and A, which is all elements that are in B and not in A. Okay, so they must be elements that are in B but do not fall in A. So if we go by what we had done earlier, let's look at the same two sets that we had earlier. So that was set B, and I think that was set A. And so we want elements that are in B but not in A. In fact, if you check carefully, you should have already seen that this element, only 9, appears to be in B and not in A. Okay? So we saw that 1, 2, and 4 were in A. So there was 1 here, 1, 2, and 4. And we had 3, 5, 6, 7, 8. So 3 was there. There was a 5, there was a 6, 7, and 8 was there. And then we had 9 appearing in B. So these are the elements in B, including 9 there. Okay, so the elements that are in B but not in A only contain the element 9 there. And so we can conclude that the set B minus A, or the difference of sets B minus A, is given by contains only the element 9. Okay? All right, let's move on. I want to just extend a little, just in case you meet a question of this nature. So in this case, we found the difference of sets B minus A. We've also found the difference set A minus B. But let's just extend a little in case you meet questions of this nature. So the next thing I want us to look at is what we refer to as the symmetric difference of two sets. Okay, so what do we mean by the symmetric difference of the two sets A and B? So the symmetric difference of two sets is denoted by that is to say that the element, remember these were the elements in A but not in B, and these are the elements in B but not in A. So if we take the union of those two sets, then we have what we call the symmetric difference of two sets. Okay, the best way to understand why we call it the symmetric difference of the two sets is to draw the diagram that represents this. Okay, so if I draw that, this region here contained, in our example, it contained 1, 2, and 4, and this region contained only 9. So when we talk of the union set, means we add all the elements here and all the elements there, and that becomes the symmetric difference of the set A and B. The symbol we use for the symmetric set A and B, I believe I've put it somewhere there, is given, I think I've put it somewhere here. So if those are our sets A and set B, then we found that set A minus B was 1, 2, and 4. Set B minus A was contained only 9. And so the symmetric set, which is normally represented by that symbol there. So when we write this, we mean the symmetric set of A and B. So the symmetric set A and B is A minus B union B minus A. And if you check carefully, that gives us 1. So basically, you're just taking the elements of these sets and adding them all together. Okay? So that is called the symmetric difference of two sets. Okay? Now, with this in mind, now let's go and answer the questions that the students had asked. So this was a question from one of the students. Show that A intersection B, everything complement, is the same as A complement union B complement. Now we're going to go by the same reasoning we've used there. So here we go. That's our set A, right? On a Venn diagram. That's our set B. Everything falling inside a Venn diagram. We don't need to draw the Venn diagram in this case because there's nothing that is falling outside. And so if X is that region there, this is inside A but outside B, and Y represents the intersection of A and B. So Y is A intersection B, and Z is in B but outside of A. We can represent this way. So set A is X, contains X and Y as the elements. Set B contains the elements Y and Z. The set in A but outside B contains Z. The set, this is the set in B but outside A, okay? In B but outside A, okay? The next one is the set in A but outside of B, that contains the element X. Then clearly we can see that A intersection B is Y, okay? And therefore A intersection B complement refers to everything outside A intersection B. So if this is A intersection B, what is outside of that? The complement means outside of it. So A intersection B complement is therefore going to be X plus Y, right? That's A intersection B. So what is, just as a by the way, A union B is also there, although we don't need it to show this, okay? So what is A intersection B complement? So A intersection B is that, and A intersection B complement means everything outside of this region that we have there, right? So the complement of that must be the region X and Z, right? And so we can show that A intersection B complement is the region that contains X and Z, or X plus Z. X plus usually means union, and therefore, and X we found is, if you remember correctly, here is our X right there, which is B complement, and our Z there is our A complement, and that means that we can remove X and Y and put the complement sets, A complement union B complement. The union there means plus, right? So when you're adding, you use the union, okay? And therefore, A intersection B complement is the same thing as A complement union B complement. As a by the way, we can also show, you notice, let me write this result here fresh. So we are saying that A intersection B complement is the same thing as A complement B complement, but the sign here changes and becomes union. Okay, that's the result we've shown there. We can also show without further proof, and you can always use this result without further proof. We can also show that A union B complement, let me use a different color. Yeah, so we can show that A union B complement is the same thing as A complement B complement, and the symbol now changes and becomes an intersection. So these two results are useful in set theory to simplify, more challenging questions. Here is the second part of the question that was asked by the students. So if the set A contains these elements and the set B has got these elements, find the difference of the sets A minus B, okay, and B minus A. So A minus B refers to all elements that are in A but not in B, and B minus A refers to all elements that are in B but not in A. So I'm going to represent this on the Venn diagram so that we can find the set A minus B. So before we do that, let's represent these elements in the Venn diagram. The first thing is, of course, to put the elements that are in both sets, so the intersection of A and B. So the elements that are in A and are in B, I can see there is a 2 there, there is a 4, and there is a 6. So there is 2, there is a 2 here, there is a 4, and there is a 6, like that. All right. Next, what are the elements other than the 2, 4, and 6? Which other elements are in set A? There is a 1 there, and there is a 3, and there is a 5. So there is a 1, a 3, and there is a 5. Okay. What about in set B? We have 2, 4, and 6 already represented inside the intersection, and so there is 8 that is not represented, and so there is only 8 remaining there. For that reason, because of that, we can now see that A minus B, the difference set A minus B, is the set of all elements that are in A but not in B, and that is 1, 3, and 5. Okay? Similarly, B minus A are all elements that are in B but are not in A, and as you can see, that is only the set containing 8. All right, and that's all you needed to know for this particular question. I hope you've understood. I'll see you in the next question.